The current artificial intelligence expansion relies on brute force compute. Tech giants are pouring tens of billions of dollars into massive, power-hungry server farms designed entirely to run autonomous agentic workloads. But this massive infrastructure build-out is hitting a hard limit. No matter how many rows of servers you rack, software watching software is an undecidable problem. By the nature of software itself, an autonomous agent's actions are unverifiable. To ensure an agent stays within its permitted boundaries, enterprises have to route its traffic back to a centralized cloud for constant auditing. Every handshake, background check, and compliance audit takes time. This continuous transaction cost is the latency of trust. When you deploy agents at scale, that audit bottleneck compounding. The operational friction of constantly verifying intent destroys the return on investment you expected from automation. Bypassing this bottleneck requires moving the verification boundary out of software entirely and anchoring it into hardware physics. This brings us to a concept called role continuity. It is the mathematical guarantee that an agent's identity, competence, and intent remain unbroken over time without requiring a single software audit. To achieve strict role continuity, that guarantee cannot live in software abstraction layers. It must be woven into the physical execution paths of commodity silicon. The objective is to construct an unprivileged on-chip hardware witness. We built this witness from a single microscopic logic gate. By stripping away the software overhead, this mechanism sustains over 7.5 million verifications every single second. Proving this works requires a strict dependency chain. We have to start at the bare metal assembly instructions, validate the physical logic, and only then scale up to the macroeconomic implications. Any claim about the global economy requires absolute technical credibility down at the individual transistor. We establish this ground truth on commodity Apple silicon architecture. This is a stock M1 chip, the exact physical hardware deployed in modern enterprise networks. The simplest unit of verification here is a 64-bit comparison, composed of one logical XOR and one hardware pop count tree. Comparing the source code with the AArch64 compiled output reveals the 64-bit pop count is not a single hardware instruction. Instead, it begins with an exclusive OR, lowers into a neon sequence for a per-byte pop count, and finishes with a horizontal add. Why not utilize AVX512 or wider SIMD vector units to process more data at once? Wide vector units carry an unmaskable cold start latency. When spinning up from an idle state, the hardware incurs a massive performance penalty. That tax applies directly to the critical first comparisons. When an agent steps out of bounds, the system needs an instantaneous halt decision. Waiting defeats the design. By keeping logic strictly within the 64-bit lane, the measured physical execution time for this ballistic gate is 0.5367 nanoseconds. That half-nanosecond measurement is the atomic unit of truth for the entire architecture. This timing is not a theoretical optimum. It includes the rotate driver and loop overhead measured directly on the host machine. Binding verification logic to a half-nanosecond hardware cycle establishes a physical baseline that software cannot spoof. Extracting these latency measurements directly from the performance monitoring unit usually hits a roadblock. Accessing the raw event registers requires root access. That makes standard PMU reads undeployable in a restricted enterprise environment where agents run inside unprivileged sandboxes. To bypass this, we extract hardware ground truth by deliberately defeating the CPU's spatial and stream prefetchers. This pointer chase uses a non-overlapping Fisher-Yates cycle across a memory buffer, creating a strict data dependency. Without a predictable stride, the out-of-over engine cannot parallelize the execution. It stalls, forcing the processor to wait on physical data transit time. Those transit times read directly off the metal, 1.8 nanoseconds for an L1 cache hit, and 151.29 nanoseconds if the processor has to reach out to main DRAM. Forcing the system to fetch from DRAM generates an 83.9 times latency penalty. That delay is an unforgeable local fingerprint of the hardware's exact physical state at that microsecond. Exploiting strict data dependencies creates an absolute physical witness that operates entirely outside the software failure domain, with zero root access required. With the physical gate proven, we scale that atomic logic up to execute massive graph traversals that track agent behavior. The primary threat to performance at this scale is global memory contention. Traditional graph algorithms use a global hash set that rapidly expands past the 16 kilobyte L1 cache boundary, overwhelming the translation look-aside buffer and crashing into DRAM latency. We eliminate this entirely, compressing working memory into a static 1,152-byte L1 resident buffer. The algorithm replaces the hash set with an additive weight model. Each traversal path is assigned a geometric decay. The instant a branch drops below a minimum floor, it dies. This bounds the recursion mathematically, removing the need to maintain a stateful memory record of where the algorithm has already been. By letting the branches naturally decay, the working set remains permanently locked to exactly 1,152 bytes. Because this fits inside the L1 data cache, the execution loop never triggers the 151 nanosecond DRAM tax. This zero-contention architecture allows a 10-core commodity processor to sustain 7.59 million ballistic graph walks every single second. Architecting the algorithm around the physical geometry of the L1 cache transforms graph traversal from a memory-bound reliability into a linear hardware advantage. This visualization shows an autonomous agent operating within a digital market. When you link this microarchitecture to macroeconomics, you see exactly how the boundary holds. The agent's semantic identity and competence are mapped directly to the physical execution paths running inside the silicon. If the agent attempts an action outside of its assigned vector, it instantly breaks its physical channel. That boundary breach is an instantaneous hardware cache miss, caught by the half-nanosecond gate. This shifts the burden of trust from software logic to physical constraints. The hardware enforces the boundary. An agent cannot step out of its lane because the silicon itself will not execute the path. In a complex agentic pipeline, over 70% of a contract's signal is typically lost to unpriced uncertainty and noise. The hardware receipt eliminates that noise, converting those unknown risks into a measurable physical boundary. By recovering that lost signal, underwriters can finally price the risk with precision. This transparency establishes a defensible floor of $760,000 per contract, backed by the physical certainty of the metal. Pricing the exact moment an agent crosses a physical boundary creates an insurmountable moat against unverified AI tools when regulatory scrutiny arrives. Stripping away continuous cloud verification drops the transaction cost of trust to near zero. Anchoring identity into the physical reality of the chip establishes the foundational infrastructure for the zero-latency economy, allowing machine-to-machine markets to clear at the speed of light.